I'm expecting a few more people to jump in the last, at this last minute here. So I'll wait just a second. Maybe wait just one more minute for people to find the link, jump in. Okay, and I'm also I'll bring up the webpage for the course just to talk a little bit about it with you all. Okay, so yeah, let's get started. So welcome to Math 219. This course has the longest title of any course I ever taught. I made it up myself. Topics in complex analysis from conformal invariance to percolation. It is a graduate topics course. And I'll discuss the content in a little bit, but I know there's a lot of people who are interested in taking this class with very different backgrounds. And my aim is to try to make the content as accessible as possible to everyone who's interested in it. So let me start by just saying a few words about the logistics of the course. So one request is that if you are coming to the lectures, if at all possible, please turn your video on. It's a lot easier for me if I have a sense of people actually being in the class. Thank you. And let's see. So in terms of the logistics for the course, I guess you've all found your way to the Canvas page and Zoom links. So that's good. Let me say a few words about how the course is organized. So I will be giving talks on Tuesdays and Thursdays, but there's a lot more available to this course. So first, I have office hours on Wednesdays from 2 to 3. And if you can't make those times, just send me an email and I'd be very happy to set up a time that works for you. And our course has a course assistant, Carl Windsor. I think I pinned his video. Carl, do you want to say hi?
Hi, everyone.
So Carl is a graduate student and he will be helping me with the course. He'll run a section on Fridays from 3 to 4:15 and have office hours from 3 to 4, also by appointment. And so all of our contact info is on the webpage under this office hours and section information here. And so as I mentioned, a lot of, there may be people with different backgrounds. If you need to fill in some background in the course, or if I went over something too fast in my talk, or if I referred to something that you haven't heard of before, both Carl's section and office hours are excellent places to go to learn about background information. So that will be maybe one of the primary purposes of the sections, is to fill in background and maybe amplify points that are done during class. And also, it's hard for me to read the chat during class. So if you want to ask a question, please just speak up. If you want to put something in the chat, then hopefully Carl will bring it to my attention as well. So he'll be helping me navigate the Zoom aspect of the course. Okay, so let me take a quick look at the syllabus. So there's a list of topics, which I don't want to discuss quite yet, but there's a few resources I want to point you to. So one is I am writing some very rough notes for this course as we go. So these are kind of retroactive course notes. They'll be written more or less after the lectures rather than before. So unfortunately, they're not really a good place to learn the main material in the course, but there are lots of books and articles, all of which are linked here. So any book that you see here or article you can see, if you click on it, you'll get an electronic copy of it. I will say that reading some of this material is an important part of the course. So the course will have actual reading assignments from these texts. And this text we're starting with is Alfor's conformal invariance. So if you were to click here, you'll see that Harvard has a copy of this available in its library, and you can download individual pages. You can download the full volume. You can also buy the book. It's available now from the American Math Society. It's pretty inexpensive. Very nice book, a real classic in the field. And then there's many other books, and as we go through the course, I'll mention which ones are best to look at. I would say that I am assuming from the beginning some background in complex analysis, and if you want to review that background, a couple of resources are the classic book by Alfor's, Complex Analysis here, also linked, and my own notes from Math 213B called Advanced Complex Analysis. So those are also linked on the webpage. And if you want to look ahead to the more probabilistic part of the course, I recommend this book by Dinkin and Yuskevich called Markov Processes. It's not quite obvious from the title, but it's a book about random walks in Brownian motion. Okay, so a couple other logistical matters. So you are supposed to have an iPad or similar kind of tablet device for this course. If we go to breakout rooms and you want to discuss something or with the other students, if you want to talk to somebody about homework problems or just have a discussion online, it's very useful to have a tablet. And if you're a Harvard student, you can request an iPad from Harvard if you don't already have one. Because they are required for this course. I'm using an iPad that was provided by Harvard. As far as prerequisites go, as I wrote, this course, although it's a graduate topics course, it's certainly accessible to undergraduates with suitable background. So the main prerequisite is basic complex analysis, preferably 213A or its equivalent. And then we will use some real analysis, probability theory, topology. But as I said, I will try to make the course, if not quite self-contained, I won't just start talking about some very advanced topic and assume everyone knows it. I'll at least provide some background about what we need. And as I mentioned, in section and in the suggested text and course notes, you can get more background if you need it. So there will be assigned reading material, as I mentioned, but also the lectures may go beyond the reading. I'm not going to cover every topic in Alfor's class, but if the first reading is Alfor's section 1, and you should really try to read all of the sections in it, even the ones that I may skip. Okay, so let me go down a bit. This course does have a Slack channel, so great place to throw out questions, get to know other students. So please take advantage of that. My expectation is that students should attend lectures regularly and work on the homework assignments. which are an integral part of the course. I should say, even if you're a graduate student taking this course for excused because you passed your quals, I strongly encourage you to look at the homework assignments. I will be trying to put together some interesting homework, not very demanding, but something that will let you engage with the material and make it real in a way that just watching lectures won't. So let's see. So I know that some undergraduates are taking the course or shopping it, and the letter grade for this course will be based on the homework assignments. Homework will be assigned every 1 to 2 weeks. As I said, I'm not trying to make this a heavy workload course. My goal is to keep people engaged in the material by having them work with it in an active fashion. And you are allowed to come to my office hours and come to the CA's section and office hours and get hints on the homework, even outlines of proofs. And you're of course allowed to collaborate. So it should be a interesting and not too daunting challenge to do the homework if you are taking the course for the grade. I also ask that if you are taking the course for the grade, please come to my office hours early in the term and introduce yourself and share your background so I have an idea of where people are coming from in the class. So my first office hour is tomorrow, and I look forward to seeing at least some of you there. Okay, so just one or two more things on logistics. So here is the list of readings and homeworks. So I've written the title somewhat telegraphically. Alfor's CIT means conformal invariant theory, chapter 1. And ACA means advanced complex analysis. So those are my lecture notes. So those are two things you should look at, either browse or review. But some of what we're going to be doing in lecture will closely follow Alfor's. So very definitely good to read that. I'm not going to try to replicate everything that's in Alfor's or in my previous notes. Not everything I say in lecture will be in the course notes. That's what I want to say. I should also mention that the course notes, since they're constantly evolving, make sure you don't just print out one version now and save it for the whole term. It only has a few homework problems in it at the moment, for example. So you always need to look at the current version, which is linked here and which is linked inside the syllabus and which is also linked on the home page here. Okay, so any questions on the logistics of the course? So this is a fresh course. I've never taught it before. So I hope you'll bear with me as I work my way through it. But I think it's a very interesting story. So let me turn a little bit to the story I want to tell, which will have sort of three main parts. The first part will be a discussion of what are called conformal invariants, which is a sort of maybe what you will learn in a third course in complex analysis. Looking at the syllabus, the topics are things like the hyperbolic metric, conformal mapping. We'll start with reviewing the Riemann mapping theorem, the Poincare metric or hyperbolic metric on regions in the plane, the method of extremal length, maybe a little bit about quasi-conformal mappings, transfinite diameter, capacity, harmonic measure. So these are fundamental topics having to do with complex analysis, primarily in the concrete setting of regions on in the plane or possibly on the Riemann sphere, occasionally on Riemann surfaces, but we won't really have very much use for Riemann surfaces in this course. It's rather a concrete and classical series of topics, and they center in large part around delicate properties of analytic functions and also of harmonic functions. So one thing I'll review is the solution to the Dirichlet problem in the plane that is constructing harmonic functions with prescribed boundary values. Oh my Lord. Hello? Okay. So the second topic, the second sort of meaty part of the course will be a discussion of random processes. And we'll start out by discussing random walks on the line and in the plane and in three and higher dimensional space, but actually discretized random walks, so random walks on a lattice. And this is a very rich topic in which you can see very transparently many beautiful ideas like Green's functions, the Poisson kernel, hitting measures, and so on, without having to do any fine analysis, as we have to do in the complex plane. But the real goal of the course is to understand how these discrete models tend, as you take your lattice and make it finer and finer, how they approximate the analytic ideas of harmonic functions. And in particular, rescaled random walk converges to a process called Brownian motion. So one of our goals is to discuss these random walks and how they limit on Brownian motion, and how this gives a kind of novel and dynamical perspective on potential theory meaning the theory of harmonic functions. And time permitting, I'll also talk about random walks in the hyperbolic plane and a beautiful theorem due to Furstenberg, the martingale theorem that underlies it. And then the final topic, which is sort of was the end point of the arc of the narrative, is the study of percolation. And there's a general philosophy in physics that statistical mechanical systems should for some reason become conformally invariant as they approach phase transitions. And that's been made rigorous in the case of the process called percolation. And so one of our goals is to describe this beautiful proof by Stas Smirnov that at least certain invariants of percolation, which is a discrete process, become in the limit conformally invariant notions. And this had been speculated on for decades by physicists who were able to derive a lot of interesting facts using this idea. And I should mention also in this regard what this course is not about. So closely allied to these recent developments in percolation is some beautiful discussions in probability theory and complex analysis. There's something called the stochastic Lubner evolution, or SLE. These are related to things like loop erased random walk, uniform spanning trees, and so on. There's a beautiful object called the Gaussian free field, which we'll touch on but not develop in depth. I should say this course is not a course on SLE, for those of you who know about it, but it's a course on foundational material that underlies SLE. So for us, it'll be much more important to understand the more classical question of how the Laplacian and random walks on a lattice converge to give harmonic functions than these more exotic continuum limits, interesting as they are. And the reason I'm focusing on this is I think these other two topics have a very broad range of applicability and it should be of interest to people who aren't going to be specialists in SLE. And yet, I think the topics will benefit those who are. Yeah, so let me finish that sketch of the material with one little bit of graphics. Let's see here. So I'm collecting, I will try to collect on the web page in this right-hand column some interesting graphics or illustrations of what we're discussing in the course. How many people have heard of the game of Hex? You can just raise your hand in the screen if you want. Who wants to explain how it works? Just unmute and talk. Don't make me call on someone. You can also just guess how it works given the picture that I've drawn here.
I think I'm not sure, but as I remember, so in each term, so you have a color. In each term, you can choose one of these cells and color that. And the goal of the red one is get from a red side to other red side, and the goal of blue player is connect the two blue edges, I think.
Right. Okay. Thank you, Tina. So, here's the game. You have a symmetric hexagonally tiled rhombus, and you colored two sides red and two sides blue, and then players alternate turns, and the red player colors some of the tiles red, and the blue player colors some of the tiles blue. In principle, you could also pass, but passing is never going to help you. And the goal is to try to create a path that goes from one side of the square to the other. Actually, let's pretend you can't pass. The nice thing about saying you can't pass is that at some point, all of the squares will be filled. So here you can see blue is about to win if it's their turn. If they take this square here, then they will have a path that goes from the upper left blue side to the lower right one. Can there be a draw in the game of hex? Somebody else want to speculate on that question?
I think it's no, right? Because like the only way that there's not a blue path like connecting two edges is if there's like a red path that like blocks it.
Right. Good. Thank you, Alex. So right. So if the only reason if you try to go across by red, the only way that can be prevented once all the squares are filled is if there's a blue path that goes the other way. So in fact, in every ending position in this game, either red or blue has won. And so this game was analyzed by, well, who can tell me who's at the left in this picture and who's at the right? Somebody else. Come on, everybody goes to movies, especially about mathematicians. Okay, let me do a little test to make sure people know how to use the yes and no buttons in Zoom. Click yes if you know who's depicted at the bottom of the screen, and click no if you don't.
There is an answer in the chat.
Oh, thank you for telling me. Who gave the answer?
Yeah, I guess Nash and Russell Crowe, right?
Sorry?
Nash and Russell Crowe, right?
Yeah, that's right. That's right. Thank you, Sardar. So this is, I'm still interested in the poll. So do click yes or no, depending on whether or not let's make it very objective. If you've seen A Beautiful Mind, click yes. If you haven't, click no. Okay, still waiting for some votes. Does everybody know where to find the yes or no? You open the participants list and it's at the bottom.
Well, I think one problem is that like Zoom updated, so like the yes, no reactions are like temporary now. So like they only last for like 10 seconds.
Oh, thank you for telling me that. I see. The votes are disappearing again. How annoying. Okay, so in any case, this, as I think most people know, John Nash was a brilliant mathematician at Princeton. He was also a paranoid schizophrenic, but he regained a lot of his composure in his later life. He won the Nobel Prize in economics and was tragically killed in a taxi accident on the way back from Oslo. I mean, from Stockholm. And but in the Princeton tea room, there were these coffee tables, and they were still there the last time I was there, that had these hexagonal patterns on them. And so the story is that he invented this game of hex. And one thing you can say about this game is that since there are no draws, and since the game is over after a fixed finite number of moves, there must be a winning strategy for one player or the other. That's a simple and intuitively obvious result in game theory, and Nash was one of the founders of mathematical game theory. But actually, in this case, it's obvious whether it's the first, second player or second player who wins. So who's the winner in this game? You think it's better to go first or second? Somebody, you have a 50% chance.
Player one has a strategy stealing, so it's player one that goes, that always wins, right?
Right, excellent. So tell me what strategy stealing is.
So whatever player two would play, if player two has a winning strategy, player one would just do anything and then play that. And having an extra move doesn't hurt you.
Right. So you can't have a strategy for player two because player one could just play an arbitrary move and then player two continues, and then player one pretends they're player two, and one of the squares has been filled to their advantage. So whatever strategy works for the second player would work even better for the first player, right? So in fact, that's a proof that there's a winning strategy for player one. And interestingly, that does not mean that anybody has been able to exhibit this strategy. In fact, I'm not aware of any rigorously proved strategy for winning this game that's not based on just some kind of exhaustive search. In particular, I think the computational complexity of designing a perfect hex player is possibly exponential. Okay, so that's the game of hex. And the reason it's related to complex analysis is not quite obvious yet, but you can see it has to do with some sort of process in the plane. But now let's play a different game. The different game is called random hex. And what we do here is we have two players who are, well, this is maybe slightly wrong, but neither player has any real goal in mind. And they just put down white or black randomly. And then we see who wins. Or perhaps even better, we play the following game. We just flip a coin for each of the different sites in the table, and we color them black or white, depending on whether the coin came up heads or tails. And then we can ask an interesting question, which is, what's the probability that black wins? And so in this original table, it's pretty obvious that the probability that, in this case, the colors are red and blue, the probability that red wins when you fill in the cells randomly must be the same as the probability that blue wins, just by symmetry. And they have to sum to a half because you can't both win. So the probability is exactly a half in this table when you randomly fill in the cells white and black. But what about when the table has a different shape? How does the probability behave? It looks like in this case, it's probably more likely that black wins than white. On the other hand, it looks to me like white, well, if white is associated to the green sides, white has, amazingly enough, won, even though white seems to be at a disadvantage because the green sides are farther apart. I'm assuming black needs to join the black sides. So one problem is, what is the probability, when you have a table that's not square, that there is a crossing between two given sides. And more important, maybe a more natural question is, well, that probability is going to depend in some strange way on vagaries of the table and the way we've cut it up into hexagons. But what if we take the number of hexagons, let their size go to 0 and take the limit? Does this probability perhaps tend to some well-defined limit? Maybe we could even calculate it for this particular table. And the physical motivation for studying this problem is that it's a model for percolation. So what is percolation? Well, those of you who were born in the 60s, of whom I see none, might have heard of something called a percolator, made this terrible coffee by bubbling water up and down through coffee grounds. Slightly more modern, when you pour coffee through a filter, if you pack the grains too tight, the water can't get through. But if they're loose enough, then the water passes through the gaps between the grains, makes it out fluidly to the bottom. So this idea of coloring sites black and white at random, this is a model for the creation of avenues for percolation in various substances. And in fact, it's one that is actively studied by climate scientists to understand what's going to happen as the ice caps melt. Especially percolation mathematician Ken Golden, I know, makes frequent trips to Antarctica to understand what's happening with the ice there. The reason being that as ice melts on the surface or deeper down, if it's possible for water to percolate down, it brings the heat down from the surface deeper into the ice, and then an entire ice shelf can collapse when some sort of critical regime is reached. And so that's one of the main issues in percolation is when is it possible to have lots of avenues that get through the holes in the ice if you start making interruptions by some sort of process which is modeled as being random. Okay, so let me maybe just conclude this warm up. This is one of the targets of the course, is to discuss the following theorem, which was open for a long time. The theorem is that the probability of there being a crossing between the black sides for critical percolation, that means percolation with probability 1/2, is what's called a conformal invariant. And what that means is if you take a region and you're trying to understand percolation in this wavy region with the wiggly sides on the left, the limiting probability of a crossing here is the same as the limiting probability of a crossing in this corresponding rectangle, where by corresponding, I mean there's a conformal map that is an analytic homeomorphism between the left-hand side and the right-hand side. And that's just an amazing fact that this process, which starts out having only a very limited symmetry, becomes symmetric under this infinite dimensional group of conformal transformations. And so that's one of our goals, although it's quite far off and it's only one of our goals, is to describe how Smirnov settled this important open problem in sort of at the boundary of mathematics, probability theory, and physics. But as I mentioned, the idea that somehow complex analysis, harmonic functions, et cetera, emerge in the continuum limit from lattice models, from discrete models of the plane, has a much longer history than this percolation problem. In particular, there's a big development concerning harmonic functions. And that will be our main goal, and then discussing conformal invariance will be sort of the cherry on top. Okay, so I think I'll stop there. There's a few more slides that you can look at your leisure, but let's see here. Let me just go back to the web page for the course. I think I've touched on everything to be discussed here. So any questions before we start talking about complex analysis in a systematic way? Okay, well, I encourage you, if you haven't seen A Beautiful Mind, to go see it. I remember John Nash, when he was at Princeton, he spent a lot of time around the math department, even when he wasn't a professor, and he eventually became a faculty member again. Okay, so for those of you who've had a Zoom class from me before, you know that I'm lucky enough to have access to a Blackboard here in the Science Center. So I'm going to switch cameras and on a sec. Okay, and now let me try to get this on widescreen. There we go. Okay, so I'm going to talk at the Blackboard. And again, feel free to interrupt me at any point. And it'll also be helpful if you feel like it, yell out that if I'm going too slow, you know all this, etc. I'm going to try to ask questions of the audience. So please don't hesitate to yell out something. It helps me to have feedback from the audience to know what's already very familiar to people and what's needs to be discussed in detail. So my goal for today is to just review some complex analysis, and with especially the target of discussing the Riemann mapping theorem. So let me start by talking about just by introducing some notation and talking about some domains in the plane and the sphere and metrics. So my notation is C is the complex numbers. So they're Z equals X plus IY, where X and Y are real numbers. So this is the usual complex plane. And then delta denotes the unit disk. So it's the set of complex numbers of absolute value strictly less than 1. And by the way, this is all in the course notes, so don't feel you need to write it down. The upper half plane is the set of Z such that the imaginary part of Z is positive. And the Riemann sphere is the convenient compact Riemann surface obtained by adding a single point at infinity to the complex plane. Now let me remind you what an analytic function is. So if we have, say, so I should say, here's a little bit of terminology. An open connected set in the complex plane is often called a region. It's useful so I don't have to keep saying the words open. If you have a map from this open set to the complex numbers, then we say F is analytic if its complex derivative F prime of Z exists at each point. Okay, so that's the definition. And I think complex analysis there's really two perspectives on complex analysis that were classical and are slightly different, but both are good to know. There was the Weierstrass perspective and the Cauchy perspective. Okay, so what Weierstrass exploited was the following amazing fact, which we won't prove, but which is proved in any basic course on complex analysis, that once your function has one derivative, it has a second derivative, a third derivative, and so on. And in fact, it can be written as a power series that's uniformly convergent on some disk. So for example, if you have an analytic function near 0, you can write f as the sum from 0 to infinity of an z to the n. It's just like a polynomial of infinite degree. And this power series converges uniformly on compact sets. And Weierstrass based his study of complex analysis and basic properties of analytic functions on this representation of the function. Now, let me give you an example of something that you can prove using this perspective. So the zeros of analytic functions are isolated unless your function f is identically equal to 0. So unlike smooth functions, which can have the property even a C infinity function can have infinitely many zeros accumulating at a point, for an analytic function, as soon as you know the function has a set of zeros that accumulated at a point, it implies the function is identically equal to 0. And the reason for this, from Weierstrass's point of view, is, well, let's suppose that this point were 0. How do we know there are no zeros nearby? Very simple. We take this function and it starts out as, say, an z to the n plus an plus 1, z to the n plus 1, etc., where this first coefficient is not 0. If f is not identically 0, there's some non-zero coefficient. And then we can write f as z to the n times an plus 1z plus etc. And this factored portion of the power series expansion defines a new analytic function, zn g of z. And g of 0 is an, which is not 0. So this function, by continuity, is non-zero if you're close enough to 0. Z to the n only has a unique 0, namely at the origin. And so nearby, the function can't have any other zeros. Okay, so that's one of the topological properties of analytic functions that we'll use all the time. Another way to say this is that the fibers of an analytic function are discrete sets. There's nothing important about 0 if I took f inverse of p. This would also be a discrete set in the plane, provided the function f was not identically the constant p. Okay, now what's the Cauchy point of view on analytic functions? Cauchy's point of view is that the most important property of an analytic function is the Cauchy integral formula. So the integral of a function around a closed loop in the plane, oriented, where the function is analytic in the region bounded by the loop, comes out to be 0. And this is actually a very, I think, a very easy theorem from the perspective of calculus. Because although often in complex analysis, we don't really think about these expressions as differential forms, they are differential form. The form dz is nothing more than dx plus I dy. And so this object is actually a one form, and you're integrating it over the boundary of a region. And so the integral of a one form over the boundary of a region is something that you can analyze by Stokes' theorem. And the key point here is that the reason this vanishes is that the two form df of z dz is equal to 0. And of course, you can verify this directly using the Cauchy-Riemann equations, but a convenient way to prove it is there's a way to write the operator d as the sum of two operators, d and d bar, And let me just write what the formal calculation gives. D plus D bar applied to F gives you two terms. There's dF, dz wedge dz. That's 0 because the wedge of a one form with itself vanishes. And then you get d bar of F times dz bar wedge dz. And this vanishes. That's the definition of F being holomorphic, is that its derivative with respect to z bar is 0. So this is also equal to 0. So that's where Cauchy's theorem comes from. I'm going to review some of the consequences of these of basic complex analysis as we go along. But what I want to do now is introduce some geometry into the picture. And the reason to introduce this geometry is twofold. One, it's going to allow us to put geometry on a great many different regions in the plane and even abstract Riemann surfaces. And the other is it's going to give us a concrete way of thinking geometrically about these objects. And in fact, we'll see that metrics themselves come up over and over again in studying analytic functions. So, so let me say what a metric is. So we'll be interested in not just any metrics, but what are called conformal metrics. So first, a metric in Riemannian geometry is a way of specifying the lengths of vectors. A conformal metric is a metric on vectors in the plane or in a complex manifold where the length of a vector depends, is invariant under rotation. That's what it means to be conformally invariant. So the standard metric on the plane, dz, this is the Euclidean metric. So it's the usual distance function on the complex plane. And a general conformal metric is given by taking a function, rho, and multiplying it by the Euclidean metric. So this will gives another conformal metric on, say, a plane region. And this function rho, we're going to allow it to, will often require this to be continuous, but will sometimes allow a rho of z to be equal to 0 at some points. We'll consider sort of singular metrics. And, but we always will require that rho of z is greater than or equal to 0. So a metric assigns a non-negative number to any vector. Okay, now, what is a metric really? How do you use it? So the typical thing you'd like to do with a metric is compute the length of a curve, or you'd like to compute the area of a region. So for example, the area of a region rho of a region U in the complex plane with respect to a metric rho is just the integral of rho squared of z dz squared over this region U. And now you might wonder, what is this dz squared? Well, this is just the complex analyst way of saying dx dy. So this is just the usual Lebesgue measure on the plane. And so if this factor rho were 1, this would compute the ordinary area of the region. And to compute the area in the metric rho, you just have to integrate rho squared over the region. Now, what good is rho? Why don't I just use rho squared all the time? It's because if I have a map, say from an interval AB into my region U, let's say that this is smooth. So I have some sort of curve in my region going from gamma of A to gamma of B. then the length of this curve is obtained by just a change of variables. It's the integral from A to B. And now I just pull this metric back. So I take rho, evaluated at gamma of z, and then I take the absolute value of gamma prime of z. Sorry, this should be of t. Gamma prime at t times dt, where t goes from A to B. Okay, so that's how one works with conformal metrics. So what are some metrics that we like? Well, on each of these regions, there's a fairly standard metric. So unfortunately, I'm going to have to erase some of this. And let me say what the metrics are. So on the complex plane, we usually use the metric dz. This is just the Euclidean metric on the plane. On the Riemann sphere, we use what's called the spherical metric, which is 2dz over 1 plus the absolute value of z squared. On the upper half plane, we use the hyperbolic metric, which is given by dz over the imaginary part of y, of z, which is the coordinate y. And similarly, on the unit disk, we use the hyperbolic metric, which is dz over 1 plus the absolute value of z squared. 1 minus the absolute value of z squared. Okay, so we will look at these metrics in a lot of detail as we proceed, but let me make some observations about them. Each of these metrics has a well-defined curvature. The curvature of the Euclidean metric is, of course, 0. It's a flat metric. What is this metric on the Riemann sphere? Well, it might be hard to guess from what's written down here, but this metric makes the complex plane literally look like a sphere, with infinity at the North Pole, 0 at the South Pole. The unit circle, complex numbers of absolute 1 form the equator. And so, in fact, its curvature is equal to +1. It looks exactly like the unit sphere. You can see that it's like the unit sphere because if z is 1 in absolute value, then this is 1, this is 1, and this 2 cancels out. So the Euclidean metric and the spherical metric agree on the unit circle. So the length of the unit circle is 2 pi, as it should be on the unit sphere. Now these two metrics have constant curvature -1. So these are what are called the hyperbolic metric. And these two regions are in fact isomorphic to one another. So again, just to review some of the background that underlies this discussion, I want to pause for a moment and discuss what the automorphisms are of each of these basic regions in the Riemann sphere. Okay, so what is the automorphism group of a region like the complex plane? What this means is it's the group of analytic maps from C to itself, which are 1-to-1 and onto. Of course, the inverse of an analytic function is again analytic. So these are the symmetries of this particular region that preserve its complex structure. It turns out that in all of these cases, the symmetries are Mobius transformations, which means that they're always of the form AZ plus B over CZ plus D. So in fact, before we do the automorphisms of C, we might look at the automorphisms of the Riemann sphere. So the basic theorem here is that if you have an analytic map of the Riemann sphere to itself and it's invertible, it has a very simple form. It's a rational map of degree 1. So the functions of the form G of Z is AZ plus B over CZ plus D. And we want that the the numerator and denominator are not proportional to one another, because then they would be a constant function. So we require that AD minus BC is non-zero. And once you've done that, you could scale the numerator and denominator to a range that AD minus BC is equal to 1. And then it turns out that composition of Mobius transformations is the same as multiplication of the matrices A, B, C, D. So this automorphism group is isomorphic to SL2C, which is the set of matrices A, B, B, C of determinant 1, except for the fact that the identity matrix gives the identity, but so does the minus the identity matrix, because minus Z over minus 1 is the same as Z. Okay, what are the automorphisms of the complex plane? They're just the Mobius transformations that send the complex plane to itself. What do they look like?
It's just like AZ plus B because infinity has to be sent to infinity.
Exactly right. So the automorphisms here look like AZ plus B, and the only requirement on these two complex numbers is that A is not equal to 0. But otherwise, A and B are arbitrary complex numbers. Now, the automorphisms of the upper half plane and of the unit disk are a little bit subtler. The automorphisms of the upper half plane turn out to be the Mobius transformations with real coefficients. And you can guess that because the upper half plane is bounded by the real axis. And so you want Mobius transformations that send the real axis to itself because they have to preserve the boundary. And that you might think that that's the only condition that's required. But on the other hand, you could take Z goes to minus Z, and that would send the upper half plane to the lower half plane and still preserve the real axis. So there's this mild condition, which is that this group is isomorphic to SL2R, again, modulo plus or minus the identity. In other words, the automorphisms of the upper half plane are matrices exactly like for the Riemann sphere, except now A, B, C, and D have to be real numbers. And in this case, the determinant condition is non-trivial because of the fact that these things are real. You can't change the determinant by multiplication by a real scalar. You can't change its sign. And so the fact that we have said positive determinant keeps the upper half plane above the real axis rather than allowing it to go below. For example, Z goes to minus Z, has the matrix minus 1, 0, 0, 1, and its determinant is minus 1. If you tried to fix it so that its determinant were 1, you could multiply top and bottom by I. Now it would be an element of SL2C, but it's not an element of SL2R. And finally, the automorphisms of the unit disk. This is probably the group people are least familiar with. This turns out to be matrices of the form A, B, B bar, A bar. And again, we can assume that the absolute value, the determinant is 1, so that says A squared minus B squared is equal to 1. So I won't say too much about the automorphisms of the disk because there is an isomorphism between the unit disk and the upper half plane. And using that isomorphism, you can go back and forth between them interchangeably. And in fact, that isomorphism sends this metric here to this metric here. So maybe before discussing that kind of isomorphism, we should say some general facts about Mobius transformations. So we have our beautiful Riemann sphere, and we have all of the complex symmetries of this sphere. And all of these other groups are subgroups of that group. So whatever good properties that group has, they're inherited by these other groups. Well, one of the main properties is that Mobius transformations send circles to circles. Not only that, but the Mobius transformations act transitively on the set of oriented circles on the Riemann sphere. So any region that's bounded by a circle is isomorphic to any other region. They can be related by a Mobius transformation. What else do we know about Mobius transformations on the sphere? Suppose I have some points. When can I send a certain collection of points to a certain other collection of points by a Mobius transformation?
You can send any 3 points to any other 3 points.
Yeah, right. Thank you, Catherine. So that you might guess, if you look at this group, there's 4 complex numbers and one of them, but there's one condition. So this is a 3 complex dimensional group. In fact, the action of SL2C on the Riemann sphere is triply transitive. So you can send any 3 points to any other 3 points. However, you cannot send any 4 points to any other 4 points. There's a non-trivial invariant called the cross ratio. So if you want, and conversely, if you take 3 points on the sphere, you can always move them to the real axis, to 3 points to any 3 points on the real axis, for example, 0, 1, and infinity. And then it's clear, sorry, that they went to the unit circle, 3 points on the unit circle, and it's pretty clear there's a unique circle that passes through them. So these two statements are very closely related. If you want to find the Mobius transformation that sends one circle to another, it suffices to pick 3 points on the first circle and then make sure they're sent to 3 points on the second circle. So just as an illustration of that fact, let's find a Mobius transformation that sends the unit disk isomorphically to the upper half plane. So to do that, I might pick 3 points on the unit circle. My favorite points are 1, -1, and 0. And then I might pick 3 points on the upper half plane. I kind of like 0, I, and infinity. And so then I could look for a Mobius transformation that sends this line to this line and sends 1 to 0, -1 to infinity, and 0 to I. And what's an example of such a map? Well, if I want 1 to go to 0, I can put 1 minus z on top. And then I put 1 plus z on the bottom. Now -1 goes to infinity. And now 0 goes to 1, which is bad. I want it to go to I, so I multiply by I. And that gives a map, f of z, that gives an isomorphism between the unit disk and the upper half plane. Okay. So now let's come back to these domains and their metrics. So when you have a very symmetric region, for example, one with a transitive group acting on it, there's often very few metrics that are invariant under the action of that group. In fact, if a group acts transitively on a manifold, and you know what the metric is at one point, and it's invariant under the metric, you can find its value at any other point by just choosing an element of the group that moves this point to that point. And in all of these cases, the action of the automorphism group is at least transitive on the corresponding region in the plane. So there's an essentially unique invariant metric, conformal metric, up to scale. On the other hand, let's look at this metric here, dz on the plane. So which of these automorphisms preserve the metric dz? Does every map of the form az plus b act isometrically on the complex plane?
You need a to have absolute value 1.
Right, that's right. So of course, z goes to 2z doesn't come close to acting isometrically. It expands distances by a factor of 2. So this group does not quite preserve this metric, but there's a subgroup that acts transitively, which is the subgroup where we require the absolute value of a to be equal to 1. So sitting inside of this is the isometry group of the complex plane, and it's slightly smaller. It's the semi-direct product of S1 with the complex numbers. Now, what about the Riemann sphere? Do all Mobius transformations preserve the round metric on the sphere? Well, that again, obviously not. If you take z goes to 2z, it'll take the circle of radius 1, the equator, and map it to the circle of radius 2, which is shorter. So in fact, most Mobius transformations do not act as isometries for the spherical metric. But there's a beautiful subgroup which does, which is the subgroup SU2 contained in SL2C. So this is a rather familiar subgroup from linear algebra. The matrices look like A, B minus B bar, A bar. Again, we can normalize so the absolute value is 1, then A squared plus B squared is equal to 1. So remarkably, this is a group, but it's also a topological space. And based on this condition, we can see what topological space it is. So what is SU2 as a topological space?
It's the free sphere.
It's the three-dimensional sphere, right? Because it's just the numbers in C2, two complex variables of absolute value 1, which is the same as the unit sphere sitting inside of R4. Okay, so again, in this metric, we have a transitive group action, but it's not the full group of automorphisms. Okay, but that's the bad news. The good news, the remarkable fact, and this is the basis of a lot of consequences in complex analysis, is that for the unit disk, or equivalently the upper half plane, the full automorphism group preserves the corresponding hyperbolic metric. So for these, in this case, the automorphism group is equal to the isometry group. And what that means is that the unit disk or the hyperbolic plane or any region in the sphere bounded by a circle has a canonical functorial metric on it. And that metric can be described intrinsically as the unique conformal metric of constant curvature minus 1 that's complete. But in any case, concretely, it is simply this metric on the upper half plane or this metric on the unit disk. And there's really not too much to verify there. And I think that this fact is probably familiar to most people, so I won't go through the calculation. But what I'd like to do is start with that as something that we understand and use it to state what is sometimes regarded as the most fundamental principle in one complex variable. So I'll rewrite the metrics as we need them. Okay. So one of my mentors and the professors I looked up to very much was Halsey Royden, famous complex analyst. And he said, compared several complex variables to one complex variable. Several complex variables is a very complicated and highly analytic subject, and it feels very different from one complex variable. This is partly because the equations for a function to be analytic are overdetermined. In any case, there's a very different flavor to it. And he once said that several complex variables and one complex variable are like the fox and the hedgehog. The fox knows very many tricks, while the hedgehog only knows one, but the hedgehog knows his trick very well. And the hedgehog trick that he was referring to for complex analysis is what's called the Schwartz lemma. So let me state this lemma in various forms. And in fact, one of the first things we're going to do in this course is examine at least 3 different versions of this Schwartz lemma. What the Schwartz lemma is going to tell us is that in suitable circumstances, analytic maps like to be contractions. And that's a very, very powerful principle. It gives us a lot of control over analytic functions. And this is the beginning of what is really called geometric function theory. I think the main idea of geometric function theory, in contrast to, say, analytic function theory, where you might use infinite product expansions and the like, is that we don't really think of analytic functions so much as functions as maps. And when you have a map, rather than thinking of it as giving you a number, you think of it as giving you a point in a region, and then you can talk about the map being an expansion or a contraction with respect to various metrics. Okay, so the Schwartz lemma has a classical statement, so let me review this for you. So the usual version is the following. This is the warm-up to the more general one. So let f from the unit disk to itself be an analytic function. Now, here's a notation I'll use very often. When I write a map of a pair like this, this just means that f of 0 is equal to 0. So we have a map between a pair of pointed region, and the base point should go to the base point, as when you're studying fundamental group and things like this. So this just means an analytic function on the unit disk. It's bounded by 1 and it vanishes at the origin. Then there are 2 beautiful conclusions. The first is that the value of f at z is less than or equal in absolute value to the value at z. So if we were to draw a circle centered at the origin of any given radius, when we apply this analytic function to it, the function gets smaller. It tends to send circles, points around the origin, to points that are closer to the origin. So this fixed point tends to be attractive for the mapping f. And the second thing is what happens exactly at the origin. The origin is fixed. So we can also look at the derivative of f at the origin, and it turns out that f prime of 0 is less than or equal to 1. So let's just have a little bit of an intuition about what's happening here. This function has to take the unit disk into itself. It could go properly into itself. It could go onto itself by an isomorphism. But somehow, the fact that it's not allowed to make the disk bigger, which is a global statement, forces its behavior at the origin to be contracted. Okay, so in Alfor's book on conformal invariant theory, this is about page 2, and he says there's no need to reiterate the well-known proof. So I'm going to give you the well-known proof. I hope you all know the well-known proof. Here's the proof. Very simple and beautiful. We define a new function, g of z, which is f of z over z. Now you see, what are we doing? We're using this Weierstrass trick, right? If you have a function that vanishes at a point, that means it can be written as a power series where the first term is z, a1z plus a2z squared, etc. And then we can factor the z out, and there's some function left over. That's what we're calling g. So we let f be the ratio f of z over z, at least for z not equal to 0. And we let it be equal to f prime of z. F prime of 0, I should say, for z is equal to 0. And then because of this expression here, you can see that all I've done is define this function g. So in fact, it's analytic at the origin. So this is analytic at 0. And if I look at let's first pretend that F was defined on the circle of Z of absolute value 1. If F were defined on the unit circle, then its absolute value on the unit circle would be at most 1. And Z has absolute value at most 1. So this ratio G is bounded by 1 on the unit circle. By the maximum principle, it's bounded by 1 within the unit disk. I'm going to say then the absolute value of G of Z is less than or equal to 1 in the unit disk. Okay, now if we want to be really careful, we realize that that was a bit of a lie. But what we can say is that on the circle of radius r, the absolute value of G is less than or equal to 1, which is the bound for the absolute value of F, and Z itself, which is 1 over r. So that implies that for any r less than 1, G is bounded by 1 over r within this circle. And as r goes to 1, that region gets bigger and the bound gets better. This bound approaches 1. And so in fact, you can make this conclusion even though F might not be bounded, might not be defined on the boundary of the circle. And then of course, to say G of Z is less than 1 is exactly to say, in this case, that F of Z is less than or equal to Z and F prime of 0 is less than or equal to 1. Okay, so that is the classical Schwartz lemma, and what it relies on is the maximum principle. So a big step was made by Pick, who observed that this statement looks slightly awkward because we've required that F send 0 to 0. Is there a corresponding statement for any map of the disk to itself? And there is. Namely, we can reinterpret this statement as saying that F is a contraction for the hyperbolic metric on the disk. That is, F prime of 0 being less than or equal to 1 means the length of a vector there gets no longer when you apply the derivative of F to it. But since the hyperbolic metric is invariant under automorphisms of the disk, that statement doesn't depend on 0 being sent to itself. The other remark I want to make is that we can also analyze the case of equality here. If you have a function that's bounded by 1 and it achieves the value 1 at some point, then it has to be constant. So if equality holds here, then G must be constant. So if the absolute value of G of Z equals 1 at just one point implies G of Z is constant. And if G of Z is constant, it just means F of Z over Z is constant, which means F of Z is a constant times Z, that constant being of absolute value 1. Similar reasoning holds here. That's just the case G is equal to 0. So in the case of equality, we have that F of Z is just a rotation, e to the I theta Z. Okay, so I've got a little bit over. Let me just finish by stating the Schwartz lemma in its sort of modern form that uses the metrics we mentioned. The theorem is any analytic map F from the unit disk to itself is either an isometry or a contraction for the hyperbolic metric. And contraction means that the norm of F prime measured in the hyperbolic metric at a given point C is strictly less than 1, and that the distance between Z and W is a strict upper bound for the distance between F of Z and F of W, provided Z is not equal to W. Okay, and as you know, contracting mappings have many useful properties. They tend to have fixed points and so on. And so the fact that analytic maps are automatically contracting in suitable circumstances has many powerful consequences. Okay, so that's a glimpse of the beginnings of conformal invariant theory. So please look at chapter 1 of Alfors, and next time we'll use the Schwartz lemma to review the proof of the Riemann mapping theorem, which should also sort of finish our review of basic complex analysis. Okay, so I'll hang out in the Zoom room for a while. Let me know. Feel free to stand by and ask me any questions after class. I'll try to do that on a regular basis. Otherwise, see you Thursday, if not in office hours tomorrow.